So this chapter is a very basic introduction to the concepts of sound and acoustics. So the chapter outline will go through just a quick introduction and then talk about sound propagation, sound pressure measurement, sound pressure level, sound power level, and then frequency analysis of noise, psychoacoustics and weighting networks, and fluctuating noise levels. So just as a brief introduction, sound is a pressure wave that moves in an elastic medium like gases, liquids, and solids. The molecules are displaced and then move back to their original position due to the elasticity of the medium. For liquids and gases, the restoring force is due to the change in pressure, while for solids, it's due to the stress in the medium. And we're going to cover just the very basics of acoustics in this section. So, sound propagation. If we consider an infinitesimal element of fluid with a longitudinal pressure wave traveling in the x direction, we have something like this, where P is the acoustic overpressure, which is the pressure above the equilibrium of the fluid, and S is the displacement of the fluid. So this element will deform as the pressure wave travels through it, and the deformed element is shown in gray, while the original is outlined in the dashed lines. So we're just showing our element again here. At the right end, the displacement is S plus partial S by partial X dx, and the pressure is P plus partial P by partial X dx, where dx is the length of the element in the x direction. We can apply Newton's laws in the x direction, and we say that F equals ma. So the force on the left-hand side is P multiplied by the area dy by dx, or dy times dx. And the force on the right-hand side is P plus partial P by partial X dx multiplied by the area dy dx. And then this is equal to the mass times acceleration. So where the mass is the density rho times the volume dx dy dz, which we could call dm, times the second derivative of the displacement, so partial s by partial 2s by partial t squared as the acceleration in the x direction. So we can cancel out this p times dy dz, and we get negative partial p by partial x dx dy dz plus rho dx dy dz partial 2s by partial t squared. We can cancel out this dx dy dz, which is the volume of the element, and we find that negative partial p by partial x is equal to rho partial 2s by partial t squared. Now, we can assume that the pressure above the equilibrium, or the overpressure, is related to the volumetric strain by P is equal to negative K delta V by V, where K is the bulk modulus of the fluid. With displacement only in the x direction, this delta V is partial s by partial x dx, so that's the change in the x direction, and then the y and the z directions don't change or are not moving. So we just have dy dz, and then the volume is dx dy dz. So this reduces to partial s by partial x. So that means that we can write our pressure as equal to minus k partial s by partial x. And then our previous expression, we can plug this in for p. So we get negative partial by partial x of minus k partial s by partial x is equal to rho partial 2s by partial t squared. So this gives us our equation in terms of s. So partial 2s by partial t squared is equal to k over rho partial 2s by partial x squared. So, and this is the wave equation for the displacement of the fluid. Now, if we want to consider the response of the pressure instead, we can go back to equation 12.1 and differentiate with respect to x. And we get minus partial 2p by partial x squared is equal to rho partial 3s by partial x partial t squared, which is equal to rho partial 2 by partial t squared of partial s by partial x. So what we've done here is just rewritten this second derivative here. And using our result from equation 12.3, we can plug in for partial s by partial x is equal to minus p over k. So now we've got negative partial 2p by partial x squared is equal to rho partial 2 by partial t squared of minus p over k, which we can write as rho over k partial 2p by partial t squared. And if we rearrange this, we get partial 2p by partial t squared is equal to k over rho partial 2p by partial x squared. And this is the wave equation in terms of the pressure. And we can see that both the displacement and the pressure satisfy the same wave equation, with the wave speed being c is equal to the square root of k over rho. And this is known as the speed of sound in the medium. For most acoustic problems, we're interested in the speed of sound in air. So usually we can treat the air as an ideal gas, which means that we can use the equation that P tilde V is equal to mRT, where P tilde is the total air pressure, which is equal to P naught plus P, where P naught is the atmospheric pressure and P is the acoustic overpressure. And T in our equation 12.7 here is the absolute temperature in Kelvin, and R is the ideal gas constant. So for air, R is equal to 287 Newton meters per kilogram Kelvin, or 53.34 in imperial units. Now the change in pressure in a gas is related to the volumetric strain as P is equal to negative K delta V over V, which we've seen already, which we can rewrite as P divided by delta V over V, which is the volumetric strain, is equal to minus K. Now these pressure variations are adiabatic, which means there's no heat exchange, so for an ideal gas, this follows this idea that P tilde V to the exponent gamma is equal to a constant, where gamma is the ratio of specific heats, and for air, gamma is approximately equal to 1.4. If we differentiate this expression with respect to the volume, we get dP by dV times V to the exponent gamma plus gamma P tilde times V to the exponent gamma minus 1 is equal to 0, which we can rearrange as dP tilde by dV times V to the exponent gamma is equal to minus gamma P tilde times V to exponent gamma divided by V. We can cancel out these V to exponent gammas on both sides, and we get V is equal to dP tilde divided by dV. We get this expression is V dP tilde divided by dV is equal to minus gamma P tilde, which we can rearrange here in this way by dividing the denominator by V. Now if we compare this equation with our previous one, equation 12.9, we see that the bulk modulus of an ideal gas is given by K is equal to gamma P tilde. We've also said that the speed of sound in the medium is equal to the square root of K over rho. So combining these, we can write that the C is equal to the square root of gamma P tilde divided by rho. And from the ideal gas law, rho is equal to M over V, which is equal to P tilde over RT. So 12.13 then becomes C is equal to gamma P tilde divided by P tilde over RT. Our P's can cancel out. And we see that C is equal to the square root of gamma RT. So this is another expression for the speed of sound in the medium. when the medium is an ideal gas. So for air, with gamma is equal to 1.4 and R is equal to 287, C, the speed of sound in air, is approximately 20.05 times the square root of T. So it is dependent on the temperature. For a solid, the bulk modulus is K is equal to E over 3 times 1 minus 2 mu, where mu is the Poisson's ratio, which is approximately 0.3 for many engineering materials, which means that K is approximately equal to the Young's modulus E. And this just shows the speed of sound in several different mediums. So for air, speed at 1 atmosphere or 0 degree and 0 degrees C, the speed of sound is approximately 330 meters per second. At 15 degrees C, it's a little bit faster, 340 meters per second. Water is 1400 meters per second. Concrete, steel, and glass are quite a bit higher, 3100 up to 5500 meters per second. So we can now talk about frequency and wavelength. So the speed of sound is related to its frequency and wavelength by these expressions. So C is equal to lambda f, where C is the speed of sound in meters per second, lambda is the wavelength in meters, and frequency is f is the frequency in hertz. So C is equal to lambda f, or lambda is equal to C over f, or f is equal to C over lambda. So humans can, on average, hear frequencies between about 20 hertz and 20 kilohertz. So for air at 15 degrees C, the speed of sound is equal to 340 meters per second, and these frequencies correspond to wavelengths between 17 meters, which would be 20 hertz, and 17 millimeters, which would be 20 kilohertz. So you can see that there's a huge range in the wavelengths that the humans can typically hear, where this ratio is about 1,000 between the lowest and the highest frequency. And we can compare this to vision, for example, where the visible light spectrum nominally corresponds to wavelengths of between about 430 nanometers to 690 nanometers, which is only a factor of about 2 compared to the factor of 1,000 for human hearing.